Hello, welcome to this presentation on multi-agent AI framework for multi-scale simulation of composite structures. I'm Avinash. I'm currently pursuing my aeronautics and astronautics at Purdue University, and I'm advised by Dr. Wen Bin Yu, who is the Milton Clauser Professor of Aeronautics and Astronautics at Purdue. So we'll quickly take a look at the background and challenges that we face when it comes to modeling and simulation of composite structures. So the first thing is multi-scale complexity. So solving these problems usually requires us to transfer information across different length scales, and in order to do that, we are required to model these structures across different length scales, which takes a significant amount of time. The second thing is fragmented workflows. So multiple tools and manual setups often force us to stitch these workflows together using converters or scripts, and this can often take time, and it has to be done in a very thorough manner in order for the workflow to get executed properly. And the third thing is data silos. So often times very high fidelity simulation or experimental data are not used for future inferences once the work is done. So in order to retain that knowledge and in order to retain that inference, having an agentic workflow where the agent understands these things can be useful for making better future decisions based on the past data that we have. In the next slide, we'll talk about this motivation and opportunities that was a driving factor for this work. The first thing is natural language interface. So with improvements in AI and especially natural language processing, a lot of the tools or softwares that require traditional codes and traditional manual setup can easily be replaced with a conversational exchange between the user and the software. So this conversational exchange can replace these manual setups often and make multi-scale simulations easier to run and configure. The second thing is accessibility and democratization. So this allows non-expert users to use advanced composite modeling tools without encountering significant training or learning barrier, and then they can learn on the go while working on these tools. So this can also broaden adoption across different teams. And finally, faster design iterations. So AI can automate optimization across a large parameter space, and this can significantly bring down design cycle times. And this can also help retain information with the model in order for it to explore such possibilities in the future as well. So in the next slide, we'll basically, before going into the crux of this work, we'll basically understand the foundation of the framework that is used here. So all of these homogenization workflows, which is the constitutive modeling workflows, are based on MSG, which stands for Mechanics of Structures Genome. So the first workflow which is presented here is basically homogenization of standard composite SGs into macroscopic models. In order to do this, we use Gmsh and SwiftComp. Gmsh is used to model these SGs, and SwiftComp is used for the homogenization. And basically we have three different types of SGs that we can model. We can have a 1D SG, a 2D SG, or a 3D SG, and this can be homogenized in order to get any of the macroscopic model properties. So it can either be a beam model, it can be a plate or shell model, or it can be a 3D model where we can get the 3D anisotropic material properties. So just as an indication, 1D SG can be used to get either the plate model or the shell model. So it can be used for any of this workflow. Same for 2D SG and 3D SG, but typically a 1D SG would be representative of a laminate SG, where the thickness represents each of the layers. A 2D SG would typically either be used for a beam cross-section analysis, so it can be a cross-section, and a 3D SG, which is shown here, like a stiffened panel, can be modeled as a 3D SG, and we can use that to get any of the macroscopic properties that are required. The second kind of workflow would be homogenization of textile SGs into a microscopic model. So in order to do this, we use TexGen to model these SGs, and once the modeling is done, the homogenization is again done in SwiftComp. So in this workflow, we have plain weave textile, a 12 weave, harness satin type weave, and or a 3D weave, and all of these can be used to homogenize these models into any of these, again, a beam-like structure, a plate or shell-like structure, or a 3D structure based on the workflow. And finally, we come to the third workflow, which is a two-step top-down multiscale modeling of textile composites using all the three softwares, GMsh, TexGen, and SwiftComp. So what we do here is we start from the microscale. So we model the microstructure in Gmesh, where the fibers and the matrix is represented in Gmesh, and this can be homogenized in order to get the properties of the yarn. And this is the microscale analysis, which is done in Gmesh and SwiftComp. And then once the yarn properties are obtained, this can be used to model the textile SG in TexGen in the mesoscale model. So now the yarn and the matrix is modeled, and the homogenization is done for those, and we can get the mechanical properties of the woven composite. So this entire thing is the mesoscale multiscale analysis. So this is the two-step analysis, and further detailed discussion of this analysis is done in the previous work of Dr. Yu and Dr. Liu, which can be referred. So now we come to the previous work which we did the previous year, and which was published in SAMPy. So the goal was to basically predict the thermal conductivity of woven composites using a function call actually. So what we did was the method was again a two-step MSG-based homogenization, where we were using this workflow to feed a surrogate model in the backend. And so what the workflow was basically the user can interact with CompositesAI, which is LLM based composites expert tool, and it can be used to talk to the tools in the backend. So which was accessed using an API using the HTTPS protocol. So once the user sends a query, the LLM is going to give the payload to the backend using a defined schema structure within the LLM tools class. And once the payload is given to the backend, so there is a decision which is done here, but we see whether the input given by the user is within the domain of the surrogate model. If that is true, then we use the surrogate model, which is an artificial neural network model here, to interpolate the result and give it back to the user. But if the user gives an input which is outside of the training domain of the surrogate model, what we do is we do a physics-based computation using the workflow I just described before. And once we have the results, we give it back to the user, and that result is also used to append to the training set of the neural network model, so that the next time the user gives a query in the same range, then the ANN model can be used to interpolate and give the results quickly. And of course, we only train the model after we reach a certain threshold. So this was the previous work, and we had demonstrated how effective it is to retrain the surrogate model and to get drastic improvements in the results. And the issue with this workflow is that firstly it basically uses a fixed SG. We have only implemented a 2D hexpack SG, and there is not much control given to the user or the LLM in order to change the settings in the backend. So it was a pretty straightforward function call, and then once the computation is done, it is given back to the user. So that's why now we move to an agentic workflow where a lot of things can be changed. A lot of freedom is given to the user as well as the model in order to set the framework for the simulation based on the user's requirements. So before we move to the workflow diagram, we'll just quickly look at what is a function call and what is an agentic workflow, and how an agentic workflow is better, and why we use skills as part of the Claude's package in order to implement this. So firstly, function call is just like a fixed schema that has a name, it has parameters, and it has a return value. So the model's role here is basically what it does is once the user gives a query, it just identifies which function to use, because since we have many tools in the backend, it just has to correctly identify which tool to call. And then once it identifies that, then it just fills in the argument as per the schema, and then it calls the tools. So the model does not have any understanding of how the tool works. It's just basically like an input parser to the tool. And on failure, it returns an error code and it stops. It does not have the capability to debug it. But when we go to an agentic workflow, a skill package, the skill which we have used, so it packages the capability with domain expertise and instructions. The model's role here is that the planner can delegate and drive the workflow based on the requirement. So and when it comes to tools knowledge, the written guidance captures how the tool can be used correctly. So it can understand once the skill is loaded in a new context, once the user opens the interface, and once the skill is loaded, the model is able to look at the skills document and understand how the tool needs to be used, and then use it accordingly. And on failure, we can map the known errors to fixes, which enables self-correction. So basically, when we build such agentic workflows, we encounter a lot of uh, errors while we are building this workflow, and each of these errors are then given in that document as a fix, so that when the next time the tool encounters these errors, it can directly correct it without any intervention from the user. So, and why skills? So skills basically refers to a package from Claude, which is a reusable on-demand expertise that turns a general agent into a specialist. So here, instead of just giving all of the information uh, to an agent, we can have the skills document which is loaded for contextually. So only when it requires that particular skill, Claude loads that document, and then based on that, it drives the model to get the results. So the capabilities can be tailored for a domain-specific task. So we don't have to. It can reduce repetition greatly. So we don't have to create the skills document every time. So for a particular agent, if a skills document is created, it can be updated, and it can be used automatically. And then So, and then of course combine skills. So if you have multi-agent like we have in this case, we can combine the skills document in the same context, and also the tool can understand the different requirements and proceed with the workflow accordingly. So this is basically just a background on what an agentic workflow would look like. And going to the actual workflow flow chart. So here what we see is that the user gives an input, which is often in the natural language, which is often as a natural language query. The planner, which is the first we can say it's an orchestrator. What it does is basically using the large language model which lives underneath. Basically, we are using GPT-4o, OpenAI's model. So based on the inputs from the user, it is going to extract the geometry, the materials, and the SwiftComp inputs. And once it retrieves all of this, it is going to make a decision on what the user actually wants. And once the decision is made, it can call either the Gmsh agent, it can call the TexGen agent, or sometimes if there are existing mesh files on disk, it can basically use that to drive the homogenization. So since the first workflow is like using Gmsh agent and then using building the model, so what we do is we create the geometry file. The agent creates the geometry file. It converts it into a mesh file. We use version 2.2 for easy conversion to SwiftComp input file. So that is created in the agent and it is stored on disk. If it's a TextGen input, what we do is we use Python scripts. So TextGen works on Python scripts. So a Python script is created and then TextGen is run in order to get the outputs in the INP format and .ori format. So basically INP format contains all the mesh details, the nodal connectivity and everything, and the material data. The ORI file contains the local material orientation for the yarn and the for the yarn basically. So based on this, we can combine these two to give it to the SwiftComp agent, which is required as an input. So next, the SwiftComp agent, what it basically does is it parses through the mesh data, either the .mesh file or .inp and .ori file. It builds the input file for SwiftComp. It configures homogenization settings. So there are a lot of different settings in SwiftComp, which the agent configures based on the input from the planner. And of course, in this stage, we also give the material data because until now, we just assign tags to the material elements. And here we actually give the material data as well. For the SwiftComp agent to do the homogenization. And once that is complete, we get the results, which is the effective macroscopic property. So the constitutive modeling will be completed at this stage. So going through each of these agents quickly. So what the Gmesh agent, the objective for the Gmesh agent is basically to build standard SG models and solver-ready meshes for multiscale homogenization using natural language inputs. So the key capabilities currently are it can generate 1D SGs, 2D SGs, for most of these applications, and it also auto creates material and boundary physical groups. So based on the number of materials, it is going to assign tags to each of these elements so that can be processed later in the when it comes to SwiftComp agent. Currently 3D SGs are under the workflow, which will also be added. And then embedded checks. So we have certain checks embedded in each of these agents. So the first check here is we see what SG is required by the user or requested by the user, and what macroscopic model is requested by the user again. So the reason why we do this is the computation of volume parameter in SwiftComp is critical to get the exact results, and there are certain rules to do that. So we check this and then we assign the volume parameter based on the inputs from the user. The second check is geometry validation. So we have simple geometry validations in the Gmesh file, which if there are issues with geometry creation, it is going to automatically check what the issues are, and then based on that, it can correct the issues. And finally, the outputs are basically a SwiftComp ready mesh files and geo files for SwiftComp to use. So the workflow is pretty straightforward, where we have a natural language input. Once the Gmesh skill is loaded, the Gmesh agent becomes active. It creates a geometry. It runs Gmesh to get the mesh. It validates the mesh, and then once the validation is complete, the mesh output is stored in the file. Similarly, we go to the TextGen agent, where the objective is to build textile composites here, again for multiscale homogenization using natural language inputs. So the current capabilities here are we can generate plain textile, plain weave, 12 weave, satin, and 3D textiles. So we can create yarn geometries from weave patterns. So the yarn geometries are parametric, so we can give the yarn with yarn spacing, the yarn thickness, and it is going to generate the textile based on that. Again, it auto generates the voxel mesh based SG models for SwiftComp. And the embedded checks in this particular agent are again the geometric parameter validation. So for example, we cannot have the yarn spacing be lesser than the yarn width, certain checks like that, in order to ensure that the textile is physically possible. The second thing is unit conversion and consistency enforcement. So a lot of units when it comes to um, the yarn geometries are given in millimeters, and so in order to have an effective consistency between the material inputs and the geometric inputs, we have a consistency check there. And the yarn and the matrix domain assignment, which is very important in order to set the correct material properties to each of these elements, that is also checked here. And finally, the SG volume computation, which is for textiles, we need to calculate the SG volume based on the inputs. So that is also done here, and the checks are made for that. So the outputs here currently are three different formats of outputs that we get from the TexGen model. So the TG3 output is mainly for visualization. It can be loaded in TexGen. The box sliced abacus meshes, the INP file is the main input for TexGen. Main input for SwiftComp, and the local material orientation in the ORI file, which is also an input for SwiftComp. So the workflow is again similar to the Gmsh agent. So the natural once the input is received and the TexGen skill is loaded, the TexGen agent becomes active. Then we generate the textile architecture. We export the voxel mesh. We do the validation of that, and then the output is stored on the disk. And finally, we have the SwiftComp agent, which is the objective is to automate multiscale constitutive modeling and extract effective macroscopic properties using natural language inputs. So the key capabilities here are it can convert Gmsh and TexGen models into SwiftComp input files. It can read the 1D, 2D, 3D or textile input, textile SGs. Currently, it supports the elastic and thermoelastic modeling. In the future, the other multiphysics capabilities will also be validated and added to this agent. The embedded checks that we do here are basically the SG dimensionality versus microscopic model consistency, which is checked in all of these agents. The material property and unit validation. Here we also do the ply orientation and layer definition. So basically, since we have the material and physical tags attached in each of these modeling agents, we need to also verify whether the overall dimensions and the overall definition match the definition for each of these layers and orientations. So that is done here. And finally, the SwiftComp input and syntax and input file validation. So SwiftComp offers a lot of different flags and a lot of different inputs which need to be correctly set, because even if there is an error in that, it can either throw an error or it can give an incorrect result. So that is all taken care in this particular agent. And also, if there are errors, there is an automatic error diagnosis and correction, because a lot of information from the SwiftComp manual is available to this agent. And since a lot of validation has been done, the agent knows all the common pitfalls and all the common errors that can pop up, and it is able to diagnose and correct on its own. And finally, when we come to the outputs, we output the SwiftComp input files is one of the outputs by this agent. And once the SwiftComp is run, then of course we output the output files as well. And we also output all of these, if it's a beam model, we for any model, we output the effective stiffness and compliance metrics. We output the 3D anisotropic engineering constants for 3D models. If it's a plate model, then we have the ABD matrices. And if it's a beam model, we have the beam sectional properties, which is an output. And the workflow for this is similar. So once the mesh files are given to the SwiftComp agent, the .se file is generated, which is the input. Then we do the SwiftComp analysis. And once the analysis is complete, the properties are extracted. And then the constitutive model is given to the user finally. So here I will quickly demo three workflows which we talked about. So here firstly we have the 1D SG to a Kirchhoff plate model, then the 2D SG to Euler-Bernoulli beam model, and finally TexGen and SwiftComp, the working of TexGen and SwiftComp for a textile model. So I'll quickly try to. Yeah. So basically, um, the prompt which is given here is I have a carbon epoxy laminate with the following stacking sequence. The material is given here as an AS4 material, and I want to get the Kirchhoff law plate properties. So this is the input given to the model, and so here it understands that this is the laminate properties which are given, and that it has to call the Gmsh agent in order to do this. So it says I have all the information needed, which is a 1D SG. The target is a 2D or plate model, and the stacking sequence. So Gmesh has run. Gmesh succeeded 9 nodes and 8 elements, which is typically a 1D SG uh, mesh. So now now the SwiftComp skill is invoked, and then SwiftComp is run. It reads the mesh data, it runs the input file, so it is ran successfully, and it checks the echo file and then does a validation, and then it reads the output.k file. So it has parsed the .k file, and it gives the output in the chat window, and it also uh, does an inferencing of why the properties are the way they are, and that is also given by the agent. So this entire workflow took around 3 minutes. I have just sped up the video for demonstration purpose. The second video is a 2D SG to get the beam properties. And so here you can see that the input is that I have a square pack microstructure with a fiber volume fraction of 60%. The material is carbon epoxy. I want to get the beam properties for this cross section. So this is the input given. So it has understood that it has to launch the Gmsh agent for this, and that it's a 2D SG to get to a 1D beam property. So the skill is invoked. Once the skill is invoked, the agent generates the square pack mesh. So it says that the mesh is generated successfully. The nodes and the elements are written here, and then it invokes the SwiftComp skill. Then the agent, SwiftComp agent reads the input file. Yeah. So once it has finished reading the file, um, it reads the .k file, and it outputs the required results here. Yeah. So this is the second demo, and the third demo involves giving a TexGen input in order to do the homogenization. Yeah, so in this case, the input is that I want to model a plane weave composite. The yarn width is 2.4 mm, the thickness is 0.4, the spacing is this. The yarn material is given here, and the material properties are also given here. And the matrix is a standard epoxy matrix with the properties given here. So the objective is to get the effective 3D stiffness properties. So here it understood that it needs to invoke the TextGen agent skill. And once that skill is invoked, it generates the plane weave mesh. Yeah, so the mesh is generated, the SG volume is displayed, and then now the homogenization is being done. So now the SwiftComp agent is invoked. Yeah, so it has completed the homogenization, and it outputs the 3D material properties, and it also gives the physical interpretation for it. So these were the demo videos. And finally, coming to the conclusion, so the key contributions for this work have been that we have a multi-agent AI framework for automating the constitutive modeling workflows. So we have specialized agents for geometry generation, textile architecture generation, and the multiscale homogenization. So the manual processing effort is greatly reduced, as well as the workflow complexity. And then we have automated inference and key insights from the results as well, which is done by the agent. The future scope for this will be integration of all these agents into the CompositesAI framework, which has a lot of composites knowledge, so it is going to improve the performance of the agent. The interactive visualization of geometries, meshes, and results. So currently we are not doing that in the chat window, but in the future we're planning to give users that visualization as well. Also have make the planner more robust for fully autonomous workflow orchestrations. So there are a lot of multiphysics uh, 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 workflows that can be incorporated in order to make the planner more robust. And finally, AI guided composite design and optimization. So we are also planning on having validated optimization designs for such agents, and that will be in the future work of this workflow. Thank you, and if you have any questions, feel free to ask them. Thank you.